So the problem is as follows. So you are given a matrix of real numbers, okay, and this 18.5 that is written here, that is the row sum. 9 point is the row sum. Similarly, these are the sum of the values in the columns. Okay. Now the question is, is the matrix rounding is possible? The meaning is, can I either round it up or round it down? So 6.3, if I want to round it up, it will be 7. If we round it down, it will be 6. So for every real number, can I make it an integer through the process of rounding, such that, so not only the matrix entries as well as the sum entries also, such that this uh, uh, row sum constant and column sum constant are still valid. Okay, say for example, like, so say for example, I make 6.3 as 7, okay, and 7.6 as, say, 7 itself, 4.6 as 4. So it is like 7 plus 7 plus 4, 18. So it should be 18. So the thing is, whether, so some, for some values we will do it round up, for some values we will do the round down, and the same thing is also true for this uh, row sum and column sum values. The question is this rounding possible? So the question is, convert each real number to an integer, either by floor operation or ceiling operation, while still maintaining the row sum and column sum constraints. If the answer is yes, then we say that this matrix can be consistently rounded. If it is not possible, then we say that this rounding is not possible. Now, given any matrix uh, of the order m cross n, which are of real numbers having their row sums and column sums, the question is there a matrix rounding possible? So to solve this problem, step one is we convert this consistent rounding problem as a feasible flow problem. Second is we have to convert this flow problem to a circulation problem. Then we have to convert this circulation problem to a demand supply or transportation problem. Finally, we have to convert this transportation problem to a network flow problem. So these are the 4 steps which we will learn here to solve this problem. And let's see how we do this. So this was the matrix, and for all the rows I create, so there are 3 rows, so I create 3 different vertices. For 3 columns I create 3 different vertices, y1 through y3, and S is the source, T is the sink. So S to x1, that means row sum, this is 18.5. So it could be 18 or it could be 19, right? So anything is feasible. Similarly, 9.8 means if it is, if you do the floor operation, it is 9. If you do the ceiling operation, it will be 10. So it will be 9, 10. So likewise, I convert all of them. Say from y3 to t. So basically, it is the third column. It is 10.9, so 10 to 11. In a similar fashion, it is assigned. So x1, y1 is this 6.3. So it can be rounded down to 6. It can be rounded up to 7. So this is 6, 7. So that is how we convert it to a so now we convert it as a feasible flow problem. Now then what we do, we will convert it to a feasible circulation problem. To do that, the procedure is from T to S, we add another edge whose lower bound is 0 and upper bound is infinity. Now to make it a circulation problem. Now after that, we will convert it to a transportation problem. Okay. So how to solve it? Okay, we should not go, better you don't look into these mathematical things. So we will explain it with this example itself. So this is 6 and 7. So lower bound is 6, upper bound is 7. And what is its inward flow? That is 18. Minimum inward flow is 18. And what is outward flow? Minimum outward flow, that is 6 plus 7 plus 4, that is 17. So minimum inward flow is 18, minimum outward flow is 17. So 1 is something, 18 minus 71, that value will be accumulated here. So x1 value is 1. Okay. So likewise, so for x1 it is 1. Take an example y2, sorry, x2. So here minimum inward flow is 9 and minimum outward flow is 4 plus 2 plus 2, that is 8. So 9 minus 8, 1 will be accumulated here. Okay. Take y2. The inward minimum flow is 7 plus 2, 9 plus 4, 13. And outward flow is 14. So 13 minus 14 minus 1 is be accumulated here. So these values are calculated here. So for x1, x2, x3 it is plus 1. For y1, y2, y3 it is minus 1. So and for source it is minus 40, because 18 plus 9 plus 13, that is 40. So 40 is outward flow and minimum inward flow is 0. Okay. So minimum inward flow is 0. So that is why 0 minus 40 is minus 40. So initially, so these are the values. Now, if you look into the network, every node initially has 0 demand. Initially, every node has 0 demand or 0 supply, whatever it might be. Now what happened? When you push 18 units of flow from S to X1, then the demand of S, initially demand was 0. If 18 is being pushed, so its demand will be 18. And since X1, 18 is accumulated here, so its supply will be 18. Okay. So what is my supply? Supply is nothing but inflow minus outflow. Okay. So inflow minus outflow is the supply. So inflow minus outflow is the supply. So यहाँ पे जो चीज भी है, these are all supplies. So now if the supply is negative, that means it is demand. If it is minus 40, that means इसका demand है 40. This is plus 1, that means supply is plus 1. y1, y2, y3 में this is minus 1, that means they have a demand. T के supply है plus 40. Okay, so that is how. So all the negative nodes are demand nodes here, and all the positive nodes are supply nodes here. So based on that, so now what we do, all these edges are 1. Why they are 1? So this is 7 minus 6, that is 1. So 6 units of flow is being pushed. Okay. Similarly, so say for example here, so 18 is pushed and 6, 7 plus 4, 6 plus 7 plus 4, 17 is being, so is the total minimum outflow. So 1 is accumulated here in X1. So that is why this is 1. Similarly, since 6 is being flowed here, flown here. So the residual capacity is 1. 1 extra units can be flown. So this residual amount is being drawn here. Okay. Now this positive nodes, basically this 1 1 1, they are basically my supply nodes. Okay. So what we do to solve this problem, we add a new source S prime, we add a new thing T prime. From S prime I will connect all the sources. X1, X2, X3, they are my source, they are plus 1. T is plus 40, so they are my source. So from S prime I have added them. From so S, the value is minus 40 here. For Y1, Y2 and Y3, the value is minus 1 there. So they are the demand nodes. So from all demand nodes, we create this. Now we convert it to convert this problem. It is already converted to a network flow problem. Now we will see that. So if you look here, like so what is the total supply? The total supply is basically 1 plus 1 plus 1 plus 40. So 43 is the total supply. Similarly, 43 is the total demand. Okay. So in T, it is minus 40. In Y, sorry. In Y1, Y2 and Y3, here they are minus 1. So 3 into minus 1 minus 3. Along with that, S ka hai minus 40. So minus 3 plus minus 40 minus 43. So 43 is supply, 43 is demand. So it is a valid problem. Now we will see that whether the feasible circulation exists or not in this graph. So what we do, we solve this a network flow here. So what is the maximum flow? We try to find it out here. So you see that here the maximum flow is also 43. So these are the things. So first I will find the augmenting one S prime T S T prime. S prime, we go to T, from T to S it will come back. Its capacity is infinite. So and from S to T prime again 40. So the value is 40. Then the second path is S prime X1 Y2 T3 T prime. The third path is the green path with S prime to X2, X2 to Y1, Y1 to T prime. So iska bhi bottleneck capacity है 1, and then S prime to X3 to Y3 to T prime, it is also 1. So 43. Now, what does that mean? That means that what this flow actually signifies. X1, Y2 में minimum जो lower bound था, that was already being flown. Along with that, X1, Y2 means this was earlier 7 point something. So it should be rounded up to 8 because one extra unit of fluid has been flown from X1 to Y2. Similarly, X2 to Y1, second row, first column. This is also rounded up. Similarly, X3 to Y3, this is also rounded up. Okay. That is why they are demarcated as red, and all other values are rounded down. So if we look into the original matrix, let's go back to original matrix. Okay. So basically, this is rounded up. Okay. This 7.6 is rounded up to 8, 4.7 is rounded up to 5, 3.5 is rounded up to 4. All other thing it remains same. So it remains 6. So floor operation has been conducted on this 6.3, 4.6, 2.3, 2.8, 5.5 and 4.5. And ceiling is done on the three values, the 7.6, 4.7 and 3.5. And we get the value. So Like here it became 8, it became 5, it became 4. Okay, and for all of this they remain same. So basically no flow has been done across, so there is no augmenting path which involved y1t or y2t or y3t, or maybe sx1, sx2 or sx3. Since they are not, no fluid has been flown through these edges, row sum and column sum, they all are rounded down. So everything, every decimal value is rounded down in this case. Okay, take, so this is not the unique way we can create the augmenting path. There are other ways of finding augmenting path also. Since there are other ways also, there are other solution exist for this problem. Let's see another solution. Okay, say for example, the first path is this red path. So maybe so it s prime t, s prime, say first we go to t. Where is my t? This is my t. This is the t. Okay, so the s prime t, t to s. Okay, t to s by this, then s to x1, s to x1, x1 to y1, and y1 to t prime. So 1 is the bottleneck capacity. So with this became 39. Okay, then the second path is s prime x2, x2, s prime, then x2, then x2, then y2, then t prime. So this is 1. Then s prime x3, x3, y1, so s prime to x3, y3, and then t prime. Third is, fourth is s prime t, s t prime. So s prime t, now it is not 40. One is being already consumed earlier. So the remaining capacity was 39. So this is 39, this is infinity, and this is 40. So minimum is 39. So 39 stored here. Then s prime x1, y2, ts. So then s prime x1, then y2, y2 के बाद t, y2 से डायरेक्ट t प्राइम नहीं जा पाएगा क्योंकि ऑलरेडी दिस बिकेम 0. y2 से t, t से s, and then s से t prime. Earlier it was 1, मतलब earlier, so 39 amount has been flown here, so it was 1. So this one is being there. So total is 43. Now based on this path value, so x1, y1, yeah, x2, y2, yeah, x3, y3, all of them are rounded up. Not only that, x1, y2 is also rounded up. So x1, y2 is this is rounded up. What else is rounded up? sx1. sx1 means the row sum. This 18.5 become 19. Similarly, y2t, that means this column sum, that is also rounded up. So this is another solution. So 7 plus 8, 15 plus 4, 19. Okay, so this is another solution for the same problem. So so for this matrix, the answer is yes. This matrix can be consistently rounded, but there are cases where you find that if the, so why it is so? Because total supply equal to total demand equal to the value of the flow. So the matrix can be rounded up. But if it is not the case, if the flow value is less than that supply or demand, then this matrix cannot be rounded up, cannot be consistently rounded. Okay, so this is a very important application, matrix rounding. Now Now we will study another algorithm. This is called maximum flow minimum cut with lower bounds. Okay, so this is not there in Douglas West book, but so this is the problem where you are given a network flow problem where every node, where every edge has a lower bound and an upper bound. And somebody asked us what is the maximum flow possible through this network. Okay, what is the maximum possible flow network? Now the thing is we cannot directly apply Ford-Fulkerson here. Why? Because in Ford-Fulkerson, in original graph since there is no lower bound, so a feasible zero flow exists. So if you look into this here, every lower bound is zero. Since the lower bound is zero for all the edges, zero can be a feasible flow. What do you mean by feasible flow? Feasible flow means it will respect the capacity constant. So 0 lies between 0 and 4, as well as it will so it respect the flow constant, that is inflow equal to outflow. So if I assign zero flow to everybody, so its inflow is 0 and outflow is 0 plus 0 again 0. So 0 is the feasible flow in this problem. Apply Ford-Fulkerson because a feasible flow of 0 exists here. So in this network you can directly apply Ford-Fulkerson because here 0 is a valid flow for all the nodes except S and T. But here if the flow has a lower bound, 0 cannot be a feasible flow because A to B 0 flow is not allowed because minimum flow is 1. Therefore we cannot directly apply Ford-Fulkerson here. Initially, demand or supply at any of the node is 0. And supply is basically inflow minus outflow. So what is the extra amount? The excess amount is being accumulated in the vertex V. So that is called the supply. And what is the capacity of this? Since 1 is the lower bound, that means 1 unit of liquid must be flown from A to B, whatever be the consequence. So rest amount, that 3 is the capacity. So upper bound minus lower bound is the capacity. So what we do to convert it to a flow problem को circulation problem करने के लिए हम लोग ये 0 to infinity edge लगा दें. Now why we should add this 0 to infinity edge? Why? So in circulation problem the definition is there is no source and no sink. So when we are discussing about circulation problem, source sink का कोई concept नहीं था. There is no source and sink, and a feasible circulation exists if the flow in a particular edge is lying between the lower bound and the upper bound. Not only that, for all the nodes V, all the vertex V, inflow equal to outflow. Now अगर मैं यहाँ पे 0 to infinity ये edge नहीं लगाता, तो add an edge of capacity infinity from T to S. Why? Otherwise inflow not equal to outflow for S and T, thereby violating the flow constant. तो अगर मैं ये edge नहीं लगाता, if I won't add this infinite edge out here, then it will never happen that inflow equal to outflow. So valid, it will always be a invalid circulation. So make it a valid circulation problem, I have to add this edge, because this addition of this edge doesn't change the value of the flow through the network, but it will help us to convert the original problem as a circulation problem. Now this problem is no longer a flow problem, it became a circulation problem. Okay, now what we do, so excess capacity is 1 is flown here, so 3 is the excess capacity, so this 3 is here, it is 2 and 8, so 2 units must be flown from S to A, so the rest of the capacity is 6. Okay, what about S? Its outflow is 2 plus 1 3, and minimum outflow, and minimum inflow is 0. So that means it is -3. Okay, so likewise I have assigned all the node values and the age values. Okay, so age consists of residual capacity, and in the node some values are negative, some values are positive based on whether inflow is greater than outflow or not. Now, so initially, so these are the supply nodes. Initially everything is 0. Okay, so if you look here, initially every node has 0 capacity, every node. So 0 supply and 0 demand, so no issues. But once you push 2 units of flow from here to here and 1 unit from here to here, and there is a 0 inflow, that means there is a demand of 3 units here. So that is represented as -3. So 3 is the demand. So these negative nodes are basically demand nodes, and positive nodes are supply nodes. Now we add two vertices, sink and source, and from source I will add the source node to all the supply nodes. So here A is supply node, T is supply node, D is supply node. So A, T and D में source से मैं add कर दिया. Similarly, other nodes like B, C and S, they are the demand nodes. So from them I create an edge towards sink. And now what I will check. So what is the total supply? This is 1 plus 4 plus 1, that is 6. What is the total demand? 1 plus 3 plus 2, that is 6. So total supply equal to total demand. Now we check whether there is a flow exist of value. So whether there is a flow value of 6 exist or not. If the answer is no, then we will tell that the feasible flow doesn't exist. Okay, let's check. So this is one path and the bottleneck capacity is 3. Minimum of 4, infinity and 3, that is 3. Then the next path, it is S, T, T to S, S to C and C to sink. So the bottleneck capacity is 1. Okay. Then I will get another path, source to D, D to T, T to S, S to C and C to sink. So again bottleneck is 1. Then I get another thing from source to A to B and B to sink. So here the bottleneck again 1. After that you see that no flow. So there is no augmenting path at this stage. So total supply equal to total demand equal to 6 and the flow value is also 6. So it is a feasible circulation is possible here. That means the problem that we have given for solving max flow min cut is a valid problem. A feasible flow exists there. Now what is the feasible flow? So 0 is not a feasible flow. That we have already argued that why 0 cannot be a feasible flow. Now this augmenting path, this flow actually assigns some value. So at this stage, if you see what is the remaining capacity. So its capacity is 6, it is 2, it is 7. So this is 6, this is 2, this is 7. So this is the residual capacity. So at this stage when there is no augmenting flow, so this is the actual remaining capacity exists in this network. So this is 6, this is 2, this is 3. So S, A, B, C, T, S, A, B, C, D, T. This portion I have copied here. And all these values are the values after we find there is no augmenting path. Now in this graph, so how we get this? So it was our original network which was given in our problem. So S to A 28 was given, A to B 14 is given. Okay. Now, so what does this mean? This means that its lower bound is 1, upper bound is 4, and since 2 is the remaining capacity, so 4 minus 2, these two amount units already being flown from A to B. Take another example like this. Its remaining capacity is 3, and what is its maximum capacity? That is 5. So 5 minus 3, 2 units are already flown from C to B. Okay, and now what is the feasible flow happening here? So that is written here. So this is the valid flow value here. So this is a feasible flow. It is 2, it is 2, it is 0. So if you look at this stage, then this assignment of flow values is actually valid. Why? Because 2 lies between 2 and 8. This 2 lies between 1 and 4. So capacity constant is being valid. Not only that, inflow equal to outflow. So what is inflow here? This is 2 is inflow, and outflow is 0 plus 2, that is 2. If you look into T, so except S and T, for all other nodes, inflow equal to outflow. So in B, the inflow is 2 plus 2, 4, and outflow is 4 plus 0, 4. Okay. Same as D, the inflow is 1 plus 4, 5, and the outflow is also 5. Okay. Now in this network, if you look into this network, what is the value of the flow? So S से कितने आउट हो रहे हैं? 2 plus 3, 5. T में इन क्या आ रहा है? 5 plus 0, 5. So 5 is the minimum flow. So feasible flow value is 5 here. That means this is, so to set a feasible flow in this network where every edge has a lower bound, zero feasible flow is not valid. The feasible flow value is 5. Now after 5 is being flown from S to T, the remaining, the residual network is like this. What is the residual network? So this is 8 is the maximum capacity, 2 is already being flown in the feasible flow, so 6 is the remaining amount, so that is why it is 6. Like BT, 0 is the lower bound and 0 is already flown, so 7 is the available capacity, available amount. D to T, maximum is 10, 5 is already flown, so rest is 5. Now in this network, now if I run a max flow, so note that this, after this slide, at this slide, whatever we have found out is a feasible solution exists for this problem, and the 5 is the feasible flow. Okay, and these are the assignment of values in different edges, which actually gives us a feasible flow value of 5. But it is not the maximum flow. It may or may not be the maximum flow. So now to get a maximum flow in this residual network, we run the normal Ford-Fulkerson algorithm, and we find something like this. So already feasible flow is 5, and this is the residual network. Now I find the augmenting path, maybe 6, 7, 5. So 5 is the bottleneck capacity. Okay, मैं ये नहीं किया, मैं पाएगा 6, 2, 7. So 2 is the bottleneck capacity. So earlier feasible flow value was 5, so 5 plus 2, it will be 7 right now. Then if I run like this, then 3 is the bottleneck capacity. Then for this, 5 is the bottleneck capacity. Okay, now at this stage there is no augmenting path. Since there is no augmenting path, so maximum flow possible in this network having lower bound is 15. Okay, since there is no augmenting path. And if I run a DFS on it, we find the minimum cut. So from here I can reach A, C. From C to D I can reach. From D to T I cannot reach. From C to B I cannot reach. From A to B I cannot reach. So the mean cut consists of two parts. In one cut S A C D there and the other cut B T is there, and this is the min cut. Now what is the value of the min cut here? The value of the min cut is okay. So the value of the min cut is this. So just a minute. Why this is okay? So maximum flow is 15. 5 is the feasible flow plus 10 I have got from that network, and minimum cut must be 50. So why it is a minimum cut? If you look into these values, you see that 4 plus 5 9 plus 10 19 minus 4 is 50. So 5 plus 4 plus 10 minus 4. Now why this is the minimum cut? So B to D, what is the value of minimum? So minimum amount, minimum 4 units will be flow from this partite to this partite. Anyway, that will be flown. So that is why this 4 is subtracted from the original value. So 4 is the maximum value that can flow from A to B. Similarly, 5 is the maximum value that can flow from C to B. So if I cut this, we have to cut it. This 4 need to be stopped. So maximum value is 4, maximum value is 5, maximum value is 10. So 4 plus 5 plus 10, 19 need to be blocked. And we know that even if 19 is blocked, B to D there is 4 amount of flow must be there. Okay, because 4 is the lower bound. So B to D itne flow to zarur hoga. That is why 19 minus 4 is 15 is the minimum cut. So that is why maximum flow equal to minimum cut. Okay, so so that is how we have solved this problem. So I stop my lecture here because this is the 2 algorithm that we need to. So I will share you the slide. Please read this slide. Otherwise, it will be tough because in the maybe in the next class, means in next Tuesday, next week, we will discuss the application of this circulation and flow problem. To understand that, it is very important that you will read these slides. Okay, otherwise it's very difficult for you to understand. So okay, so I will share you the slides. Thank you.